Howdy, everybody. Thank you for joining. I'm sure more people will come in as we get going here. But today we're going to be talking about how to design for plastic staking. If you haven't figured it out already, we're trying to do our best to engage and interact. So the chat is how you can talk with us. So you can type a message in the chat. We'll do our best to see those messages and read them and respond to them. So if you have questions as we're going along, please type them in as they come to mind. We will have time for questions at the end as well, but we're going to do our best to answer questions as we go. In the room with me today and also presenting is Katherine. She is our inside sales engineer who has how many years of experience in the lab?
5.
5 years of experience in Extol's process development center. And Sean, who is our design engineer. And how long have you been doing that?
Almost 6 years now.
6 years. All right.
Just barely beat me.
And then I guess I should probably say I'm Jason, and I am our marketing communications manager and account manager for some of our customers. So without further ado, let's get started. Here's the presenters in the room. Probably should have had this slide up while we were introducing everybody, but you know, we're past that. Here's our agenda for today. We're going to do a staking overview where we talk about what is plastic staking generally. So there's lots of different staking technologies, and we'll talk through what they are. Then we'll go into the basics of 2 specific technologies that are proprietary to Extol, both InfraStake and nanoSTAKE. Then we'll talk about the differences between and where you might choose InfraStake, where you might choose nanoSTAKE, and the advantages of each of those. We'll talk about how to design for each of them, which is probably why most of you are here. How do you design your plastic part for plastic staking? And there's some differences between InfraStake and some differences between nanoSTAKE, and these design guidelines fit a lot of different plastic staking technologies. And then lastly, we'll save some time at the end for questions and answer. Hopefully we'll have time. If we go long, it'll be okay. If you need to jump off because you're only planning on a half an hour, that is okay because we're recording today and we'll send out the recording afterward. It might take a little while. It'll either get the recording at the end of the day today or sometime tomorrow. All right. So, staking intro.
So just to kind of generally talk about staking and maybe the different technologies that you've seen out in the field or in the industry, from left to right here, we've got Hot Punch, which is kind of the most basic staking technology there is. As you can see, there's both the technology and then underneath kind of like a little image of what the stake looks like in the end. So if you've used Hot Punch, you know that in the end, the stake's a little ugly, a little stringy, but it gets the job done. It's quick and it's there. Then we've got ultrasonics, which is right next to it. Again, it's super quick, but the downside is it's often not very pretty. Oh, Jason, you went on mute.
I did.
That's what Paul's saying.
Uh-oh. Can people hear me? Say something in the chat if you can hear us.
Is it going off of my computer?
No, it shouldn't be. Okay, good. We got some people that can hear us. Perfect.
Sorry, Paul. Ultrasonics, the downside though is that you often get a stake that is not very appealing to look at, maybe a little off-centered, but still, again, the 2 pieces are together, so in some cases that's the perfect technology. Then we've got Hot Air, similar, still not super visually appealing stakes for the finished product. And then as Jason said, to the right, we've got 2 of our proprietary technologies, which are InfraStake and nanoSTAKE. So InfraStake, you can see, uses the IR to bounce on the inside of the concentrator, which Sean will talk about in a little bit. And then you've got that cute little picture underneath of a nice round little dome, a beautiful stake. And then next to that, we've got nanoSTAKE. And you can see just the size difference alone of the module to the rest of the technologies, and then as well as the staking capabilities for the bosses. So you can get it real close to part walls and stake some really tiny little components together. So those, in a nutshell, are the different staking technologies. Then we've got the different types of heat transfer that the different technologies use. So from a real general description, radiation is heat transfer through waves. Convection is heat transfer through gases or liquids. And then conduction is heat transfer through touching.
All right, so InfraStake basics. Wait for the camera to get on.
Come on.
Oh, there it goes. Perfect. All right, so what I have here is a little intro, a little video, if you will. I'm going to press it and I'm going to play it twice, actually. But this is the InfraStake technology. The video will show the staking module coming into position, heating the stake while applying a low flow cooling air. You probably hear that. And while it is staking, the plastic is being formed by the anvil or the punch on the inside and retracting. So I'll just play that again. You can see it happens pretty quickly. So here's a bit of a graphical representation of the process. So as the first image under a clamp is just the module, the InfraStake module coming into position. And the second image is the halogen quartz lamp applying the infrared, bouncing off the internal parabolic surfaces and really focusing on the plastic. That becomes semi-molten. And then the plastic will be formed in form stage. You see the anvil has stricken the part and formed it while it's molten. And then high flow air will turn on and really rapidly cool that down. So once everything is complete, the InfraStake unit will then retract. So InfraStake has a couple different standard modules, if you will. The smaller of the two on the left is for tight applications. As you can imagine, it's smaller, so the lamp output that we just talked about is only at 35 watts, versus the other two are at about 100 watts for output. This can affect cycle time and also the ability of how big the boss that can be staked for these different technologies. The other difference between the two of them, the question is which one in the video was it? And I believe that was the IS-32.
Yep.
So the difference between the IS-125 and the IS-32, they're about the same diameter. It's really just the sensing. There's a couple different options for that gold cone that we'll talk about in a minute, but they're pretty similar. So what is modified on these modules is the, again, gold tipped cone. You can see here we have a couple cutouts and they're also able to be closed out is what we call it. You can see that sort of welded in piece of yellow anodized aluminum. And those are there to protect the part. As you can imagine, closing out and adding cuts to these does alter the parabolic surface and can change the amount of light able to hit the boss and alter the cycle time. A lot of cases, if the cuts are minor enough, it really doesn't play much of an effect.
And why do we modify those concentrators, Sean?
So we'll modify these to get as close to the part as possible. So sometimes there are interferences that might be present when you place in, like, say, a sample module that we have available on our website. And you might think, well, I can't use that technology. But in reality, we can alter things to make it fit better.
Great. Any questions about InfraStake before we move on? Perfect. nanoSTAKE is next.
To nanoSTAKE. So our second technology that we're going to focus on today is nanoSTAKE. I'm going to show you a fun little video on the next slide. And like Sean did, I'm going to play it twice. So don't panic if it buffers a little bit or anything, but I'll just talk through what's happening here. So on the left, we've got the thermal view of what's happening to the module during the staking process. And on the right, you have what's actually happening, what we can see going on. So the heater inside the module is rapidly heating. Once it reaches its temperature, the module comes down, makes contact with the boss. Once it reaches its final position, it will then dwell, then retract. Like I said, super fast. We'll play it again. There's the cooling air turning on, rapidly cooling the heater. And something that's super cool about nanoSTAKE that may not be super common with other staking technologies is that you can actually touch the module afterwards. I've used a hot punch before, and let me tell you, you do not want to touch that afterwards. So that's something that's super cool about nanoSTAKE. I mean, it adds safety elements, different things like that, and that's where the reduction of the stringing of the material comes from, because we're cooling it before we retract the module. So something that's really neat about our specific staking technology. Here's the process broken down a little bit. So can you see my mouse? Perfect. Mm-hmm. Here on the left, we've got the heating. Like I said, that little heater on the inside rapidly heats to its programmed temperature. Then the module will come down until it reaches the mating component. Then it will sit and dwell for whatever your programmed amount of time is. The dwell allows for the molten material to fully flow throughout the cavity to fully pack out the punch. Any materials you cannot nanoSTAKE? This is a great question. So there are particular materials that are better suited for nanoSTAKE. Oh, another good question. I'm going to finish the material answer first, because also size limitations is a big thing for nanoSTAKE as well. But like I was saying, there are some materials that are really well suited for nanoSTAKE. Specifically, we see small bosses, like use it for tight little areas, small bosses, things that are maybe heat sensitive like PCBs. Anything along those lines are a good fit for nanoSTAKE. But the material, the actual bossed component, does have some limitations. What we do is, if we're concerned maybe about the compatibility with the module, we will test the material. So you can send your parts in. We'll stake it with a punch we have in-house, or you can purchase a custom module for your application and we'll assemble parts for you, just to get a feel for material compatibility with the module. The next question was size limitations. There are size limitations, and Sean's actually going to go really in depth about what they are later on, so I don't want to spoil his portion of the presentation. So he'll get to that in a bit. And then, oh, this is an interesting question. Given typically nanoSTAKE applications require smaller bosses or have smaller bosses, how many stakes do you need to compensate as opposed to InfraSTAKE, maybe to get similar strength out of the two? So Sean's going to go a bit into the strength calculation as well, but we have kind of a general rule of thumb for calculating what stake strength is going to be. And with nanoSTAKE, there's a slightly higher safety factor than with InfraSTAKE. So you just probably do the math, kind of figure out how many stakes, like you said, you need to compensate for one traditional InfraSTAKE point. So, I mean, apparently you're getting all the good content today.
Don't worry, we'll get there.
Sean will get there, and now I'm really jealous that you get to talk about all the fun math, but whatever. Feel free if you've got any other questions. I'm happy to answer them or pawn them off on Sean later. Yep. But so, like I said, we've got the form portion of the cycle where the material flows throughout the cavity and packs out the punch. Then once it has dwelled for its set period of time, the module will cool to its set temperature. Like you can see the little cooling air is blasting out there. That's both to cool down the heater itself and the material inside the punch. And then after the programmed in temperature has been hit, the module will retract, and that's when it's safe to touch. So on the screen, you can see our kind of two different, not technology, they're just different parts of the nanoSTAKE module. The left side is the base module, so if you're buying spares of anything, this is what you will receive. It is the core base module. It's got the LED attached, so that piece can be replaced on the total cylinder. The cylinder is on the right side there, and then if you order a package or a machine, that whole unit will be what you see, not just the tiny little base module. Got another question. Is the cycle time longer on nanoSTAKE versus InfraSTAKE versus sonic welding? This is another great question. I'm loving it. So nanoSTAKE is typically like I said, really small bosses. InfraStake can do those small bosses, but often you've got a really tight area you need to fit the module in, so maybe InfraStake wouldn't fit. In those cases, seems you can't fit InfraStake, hypothetically. nanoSTAKE is faster because you can't put InfraStake in there in general. But there are times and situations where one technology is more suited, maybe based on material, boss size, different things like that, where cycle time will be highly dependent on that specific application. So it's hard to say, you know, one for one, which technology is going to be faster without knowing more about that specific application. Like I said, the team that will actually stake together the parts and, you know, test them for you, they'll also provide cycle time estimates if requested. So if you've got a question about your specific application, you want to shoot us material color, general boss dimensions, and material type, we can give you a better estimation.
Robots.
Oh, yes, we can stake InfraStake and nanoSTAKE on robots. In fact, that's what we do in our lab on a daily basis. It's pretty fun driving those robots around. But, I mean, then you crash it, and then it becomes a whole thing. And then you ask Sean to make you a new module, and he doesn't always like that. But to answer your question, yes, they can be put on the end of robots. Did I answer everything?
I think so.
Okay, perfect. So, like I said, different applications require different punches. So the way that InfraStake is customized is by modifying the concentrators, well, and the punches as well for volume. But anyways, the way that we can modify nanoSTAKE is to kind of offset the punch or, you know, offset the punch from the heater so that you can kind of reach down into a tighter little cranny. So the left case is maybe your boss is really close to a part wall. We can offset the punch cavity so that we can get a little bit more clearance for the module from the part wall to kind of fit it in a tighter space. That middle picture is showing what I believe is our smallest stake to date. If I'm remembering correctly, that stake was like a 0.5 millimeter tall, really tiny. But that's just to show kind of the big range of different boss geometry we can match. And then the module on the right, like I said, shows that we can offset the punch cavity from the heater itself. Maybe in this case, there were little PCB components that we wanted to make sure that the module wouldn't come in contact with, or the heater area wouldn't come in contact with, so we can have the punch cavity sit off of the module. And then this is going to be the bit that all of you were waiting for, I'm sure.
Great. So how do you know which one to use? The big question. So before we get into that specifically, I wanted to really point out the differences here. So InfraStake is a non-contact. You can think of that as the radiation or like fire heat transfer. And then nanoSTAKE is the contact staking. That is more like a, let's say, a frying pan with butter on it. The main difference between the two is InfraStake will utilize the IR energy to heat the entire boss inside and out all the way to the core, where nanoSTAKE is only really set up to touch the boss, and that's where the heat is localized, and as it's forming, that will move downward. So now that we have that under our belts, Katherine mentioned a safety factor. So how strong does your joint need to be? And then from there, we can sort of determine how big of a diameter that you might need for the actual post. So at Extol, we really drive everything based on that diameter. So this is really a key function here. So you can see here that the safety factor for this particular formula is 1.2 for InfraStake and 2.5 for nanoSTAKE. Again, this is a very general approximation, but you can tell that because of the heat transfer mode, nanoSTAKE is a little bit weaker than InfraStake in comparison. So, design guide, boss design. There's a lot of stuff on this image here, but in general, this is a guideline set up for both InfraStake and nanoSTAKE. And in general, it can probably be used for other technologies as well. But everything is, again, based on the originally determined cross-section or the boss diameter. The then if you look at, say, this through hole, that's pretty important. That will really drive your strength for tensile strength. And there's a little bit of a range that we'll show later on, but how tightly can you design that through hole of the mating part to the boss OD? A couple other things to highlight here is there's a little bit of a range that we like to see for maybe solid bosses. Again, also with hollow bosses with the core pinned out here. And then we can also do tabs. So anything that is a little bit rectangular, if you will. So here is a little bit more in detail. There's a couple slides coming up here for the IS-32, the IS-125, and the ISM, as mentioned before. The table here for the IS-32 is really just helping to explain the maximum size mainly. You can see it here highlighted in yellow. On the left here is the solid pin, the hollow pin, and the tab shape. A couple of dimensions to highlight here are the 12.7 millimeters tall for the solid pin, maybe a 9 millimeter wide or in diameter for the hollow pin, and then maybe a 3 millimeter for the tab shape, and that's for thickness here. These are maximum sizes, just to mention. So the IS-125 is the same concept as the IS-32. The difference here being the 9.5 millimeters tall, and everything else is pretty much the same, minus the, again, a little bit shorter for the tab shape. Got a question.
What dome design are the guidelines based on? Can there be a larger gap between boss and hull if a wider dome is used? Ooh, good question.
That's a good question. I actually have something similar to that coming up in a slide, so hopefully I'll be able to explain that a little better. More to it. So to wrap up the 3 different types of InfraStakes, so here's the ISM 20 module. This one's a lot smaller than the other ones. We'll highlight the fact that it has about a 4 millimeter height and maybe a 4 millimeter diameter. This is due to, again, the smaller wattage bulb at 35 watts. And you'll see on all these slides that max size is not recommended for optimum strength. Bigger doesn't always mean better, as a larger boss means a longer cycle time. So the trick is to balance both the boss size with what is needed for both optimized strength and cycle time. So this is the nanoSTAKE table. This is a little bit different than the InfraStake, where InfraStake was highlighting max sizes. This is more so a suggested max. We've done stuff outside of maybe this solid boss for nanoSTAKE at a 4 millimeter by 4 millimeter. That's a good question. When do you choose a tab shape? So it's really customer dependent and maybe your customer driven, right? But what I've seen in history is maybe using a tab shape for situations where you want to help with vibration. Having that longer cross section of a tab versus a round shape, round shape would help with that.
I think too, sometimes depending on the draw of removing the part from the mold, sometimes customers can't actually mold like a solid round boss in. So we'll see some, don't we call it like a shark fin or something like that, when it has to match the mold or the draw of the mold. So that's another scenario where sometimes tabs are used that I've seen.
Yeah.
And then just one more reason would be if you have a variation in your part location and you need to be able to compensate for left, like to one direction, you need to be able to have the mating component fit in a lot of different areas. If you do a tab, you can still get some decent retention because you're forming that tab over and clamping on the skinny side of your tab, and then you can leave the ends kind of open, and it allows for a lot more variation part to part.
Some people even will choose a tab shape for concerns with heat sink with their mold. So back to this table here, as Katherine mentioned, we've done things at 4 by 4 millimeters tall in diameter. down to a 1/2 by 1/2 millimeter, very small. We've even done a little bit bigger, but we've tested that and proved it out for those types of situations. This is the same as the previous slide, but more so for the rectangular shape. We can go a little bit taller with this. Again, volume is a little more concerning with nanoSTAKE just to help with the conduction heat transfer. So while we can go a little bit taller in this circumstance, the width and the volume is about the same. So you can kind of optimize these to whatever you might need. So these are, again, not a catch-all, but just a range and a suggested maximum.
So up to this point, we've talked a lot about what the boss looks like, but what's also, weld tab that has reinforcement ribs along its wall.
Yes, yes, you can.
Absolutely.
Yep.
Nice and easy. We've talked a lot about what the boss looks like, but also there's value to what the mating component looks like. So as you can see on the left here, this is our best case design, flat boss component, flat mating component right on top of it. So the boss being perpendicular to the mating component is key here. You'll see that in the middle too. In this case, you know, maybe the part wasn't actually flat, maybe there was a curvature to it, but still having that step in the mating component so that the boss is still perpendicular is still great as far as our punch design goes, concentrator design that Sean would do, and then just strength. You're going to get the best overlap between the stake and the mating component in the two cases to the left. Now, we do see the case to the right where the boss is at an angle from the mating component. This is not recommended, but potentially if you can't avoid the situation, we can review it and kind of highlight concerns or do feasibility studies to figure out if we can actually make this happen or not. So the issue, what happens here is your punch comes down and it can either clip off, you know, a portion of the boss so you're not fully staking the volume that's present, or what'll happen is the stake will get misaligned from the mating component, so you won't get adequate overlap for the mating component. So this section over here might not have any stake covering it all, which is not great for your stake strength or the appearance. So that's why we don't like that design. Like I said, we have done it in the past and we will review it if we need to, but if possible, whenever possible, please use the left two cases. So another bit on how to kind of your application. Fear not, we have a team that will review it just in case you are a little unsure. We're happy to give recommendations for the technology, but just to kind of give you an idea of how we pick one over the other. So as you can see here in the corner, the nanoSTAKE modules are a heck of a lot smaller than an InfraStake module. It's no surprise they're 8 millimeters in diameter, not 20 like InfraStake. So we can fit them a lot closer together, so you can stake bosses that are closer together with the technology. But that being said, even if you can't afford the real estate of, say, 34 millimeters of clearance between your bosses, what we can do is we can tip our modules up to 15 degrees in order to kind of fit them a little bit closer together. And even with the 15 degrees, we've done more of an angle in the past, but like I said, that's an area where we'd have to test it and want to validate that there are no issues.
Hello.
Hello. And then, like Sean said earlier, another thing we can do to get kind of some more real estate with InfraStake spacing is we can cut the concentrators to avoid tall part geometry. So we can also do a combo. We can cut the concentrator and tip it. But I mean, whenever you're sacrificing material in your concentrator, there's risk of uneven heating of the boss. There's risk of kind of misshaping the boss because you're not fully heating said material, or longer cycle times. So those are all impacts which would be highlighted in a feasibility study. And then if it's really a concern, we'd happily test parts for you. So it's not an uncommon thing that we see or do. So this picture is to show kind of the different ways that you could mount an InfraStake module. Our ideal because we like to live in an ideal world, is perfectly up and down. We want to heat the boss straight down, stake it, works like a gem. Upside down is another case that we'll get requests for, which we can do, but just to kind of warn you, there's potential for the material to drip into the concentrator, so you'll have increased maintenance and cleaning with your module. Another thing is if the machine's not running, the dust will settle in there, and depending on how long you're going between running it and cleaning it, you might get a lot. So like I said, increased cleaning and maintenance. The similar risk is run with the right two cases, kind of staking at an angle or staking horizontal. You still risk material dripping into the concentrator. But specifically for these cases, what can happen is you'll heat the boss, and then as that material heats up, say it's a really tall black polypro boss, that material will start to sag. So when your punch comes down to hit the boss, but all your material has drooped out of the way, you might miss a lot of the material. And we can't compensate for that because, I mean, the material is moving, not necessarily the technology. So that happens in these two right-hand cases where the material can move. So again, we recommend some testing to see kind of the impact of mounting at an angle. So nanoSTAKE, on the other hand, can be mounted at any angle you please, as long as it is perpendicular to the mating component. So this is crucial for nanoSTAKE. You have to have the module perpendicular to the mating component. So you can see we can stake normally, we can stake upside down, we can stake over here, we can stake horizontal, except for this middle case where the boss is not perpendicular to the mating component. We cannot compensate for that with this technology. There's just too much variation, too much load on the module, so we stay away from it.
So what can your stake look like? And how do we determine, what geometries might be used to make that shape? So InfraStake is kind of a dome shape as a preferred way of designing your finished shape. We have done loads of other different shapes as well, some of which are kind of shown to the right. nanoSTAKE is more of a puck shape. We try to do that for situations to keep, I guess, the heat time optimized. So the closer we are to the heater, the faster that the conduction can take place. These are technologies that do not have a standard design. There's no standard dimensions that we give out. We design your tools to fit your individual bosses per the individual location. Is it possible to share the presentation?
Yep, we'll be sharing it after the call.
Okay, so the elongated dome on the right side is more for tabs. We steer towards using that shape for tab shapes. And then I wanted to mention the rosette as well. This is for situations for InfraStake where there might not be adequate material to cover said through hole. So here we have a couple of graphics. The nanoSTAKE tip have a special coating.
Oh.
We have done special coatings for glass-filled material projects where we can apply a coating to help improve the longevity, because as you can imagine, glass inside of plastic will kind of maybe deteriorate over time, the tool. So that's really what we offer for that technology.
But not on every one.
Right.
Yeah.
That's not a standard practice, I guess, if you will.
So this slide goes back to the question about hole size and, just putting a large dome on top.
Right. So the tighter the through hole, again, to the unformed boss OD, the more cross section will be available for the plastic above the mating surface. So having as you can see on the left side, an ideal shape will provide the best tensile strength for your project. This is both for InfraStake and nanoSTAKE. Large through holes can cause a larger material overlap. This then would cause situations on the right where you can see, a weaker cross section, because we're really depending on the sharp edges of that through hole upward through the plastic. So the less plastic above that point, a little bit hard or a little bit easier to pull through, if you will. Here's a kind of a top-down and a isometric style view for a finished shape. And what we're trying to explain here is the dark blue section right here would be your unformed boss. We try to have a little bit of a range, as mentioned before, of about 10 to 25% bigger for the through hole than that unformed boss. Your overlap, so your finished shape, will be about 35% larger than the resulting through hole size. So that's again, pretty rough estimate. There's dependencies on volume and maybe tilting that could be taken into consideration. But the result will be these two situations on the right. So another thing to note, Extol will generally design your product to have about 95% fill, cavity fill of the unstaked boss. So that will provide a little bit of flash, but the reason behind that is to ensure that there's a complete stake every time. So allowing that little bit of wiggle or tolerance in there of 5% will ensure that.
So just a quick side-by-side comparison of the two technologies to kind of wrap us up here. So InfraStake is typically stronger than nanoSTAKE. Sean went into earlier why that is, and that's due to the type of heating. So feel free to go back to that if you have any questions about why. Like I said, we can get better strength with InfraStake, which means we can also often get parent strength material with InfraStake stakes. So the cycle time, again, this is a little bit hard to kind of quantify without parameters of the specific project, but we've got a team who's happy to estimate cycle time for you if you have a limitation there. Part clamping, InfraStake has integrated part clamping, which is super beneficial to ensuring a tight stake at every single point individually. And then nanoSTAKE does not have integrated clamping, so we often recommend auxiliary clamping for those applications. Maintenance, I touched on briefly with orientation, but even in a perfect world, when we're staking top down, there's cleaning required for InfraStake. For nanoSTAKE, there isn't any. And then sensitive parts, both technologies are safe for A-surface components or other sensitive components like PCBs because there's no vibration. So then we got material color, InfraStake, because it's absorbing the IR. Color is a big deal. So please specify your colors when you want cycle time estimates or submit applications because it heavily impacts the feasibility, not the feasibility, but it heavily impacts the application and whether or not we can do it in your cycle time. Versus nanoSTAKE, because it's via contact, there is no effect that color plays. Oh, Sean, can you speak to cleaning for InfraStake?
Absolutely. So with the InfraStake product package, we'll give you like an award glow finish and cleaner. And then you just take like a glasses cleaner cloth and you can just kind of clean the parabolic surfaces for those. And they come with just about every package that we give out.
I believe there's a video on our website too, and I think the video is only like 10 seconds long because it's just super quick to polish it off and throw it back on the module. And then lastly, module size. InfraStake has two different sizes, both in 20 millimeters and in 32 millimeters. And the nanoSTAKE is just one size module. It's 8 millimeters. So that kind of highlights the major differences between the two technologies.
All right. Well, we went through a lot today, and then we also went over our time. Sorry about that. But do you have any more questions? Are there questions that you asked during the presentation that you feel we didn't answer adequately? Because let us know, and we will see if we can try to address those right now. see what is. Oh, and then before everybody starts jumping off, we have some resources here that you can use. Our applications lab, you can review your design and get feasibility studies on your actual application. So you can feel free to email any one of us or send an email to sales@extollink.com to send that stuff in. And of course, you can peruse our website when you get this presentation from us later. These will be links that you can click on, or you can just go to our website and look at InfraStake and nanoSTAKE. So did we get a question coming in? Setting up the heat stake program is an iterative process. Are there some guidelines which can be used to define the settings? Yes, we have actually 2 videos available on YouTube, and I'm not sure if they're posted on our site directly or not, but we can share those where we talk about setting up nanoSTAKE and we talk about setting up InfraStake. And
There's a user manual as well for
there's also a user manual
as a supplement.
Yep.
And then there's the processing assistant for InfraStake as well, which I think you just input kind of your general boss dimensions, the color and the material, and I think it spits out kind of some parameters for you, right?
Yep, and then it like runs you through the iterative process. So you stake something, and you observe the process, and you just answer a couple simple questions, and then it'll adjust the settings for you and dial things in. So that's with InfraStake. Yeah, thank you. Yeah, thanks everybody for joining, and have a great day. If there's more questions, we'll stick around for a couple more minutes.